Hello, and welcome to the Sleep Science Podcast. I'm Penny Lewis, a neuroscientist specializing in sleep and memory and the presenter of this show. In the podcast, we talk about all things related to sleep, from dreaming and sleepwalking to what sleep does for our brain and our body and how we can get more out of our sleep. Please see the Sleep Science Podcast webpage for details. Before starting, I'd like to flag the fact that my lab is currently advertising 2 new PhD positions. These are aimed at the study of memory consolidation in sleep. I'm open to proposals that use behavioral experiments, EEG, fMRI, computational modeling, and/or the use of machine learning to identify reactivations. Please feel free to contact me if you're interested and have a look at the formal advertisement on findaphd.com. I look forward to hearing from you about it. Okay, so today we have 2 guests in the podcast, Professor Manuel Schabus and Professor Kerstin Hoedlmoser, both from the Center for Cognitive Neuroscience at the University of Salzburg. In this episode, we discuss their work on the development of sleep in babies, first discussing what baby sleep is like and how it differs from sleep in older children and adults with regard to sleep oscillations and stages, and then also talking about why we think this is. We also look at the difficulties of recording sleep in babies and some of the other methods used to assess baby sleep. We then look in depth at the development of sleep spindles in babies and go on to discuss the difference between fast and slow spindles and their importance in connection with memory consolidation and learning. We then talk about the importance of coupling between sleep spindles and slow oscillations and how this coupling alters as we age and develop and why it's important for memory consolidation. Finally, I'd like to add that this episode is particularly near and dear to my heart as I was heavily pregnant at the time of the interview, and I now have a 3-month-old baby literally sitting on my lap. You can probably hear him. I hope you find the conversation as interesting as I do. Welcome to the Sleep Science Podcast. It's a pleasure to have both of you, Manuel Schabus and Kerstin Hoedlmoser, and I'm really looking forward to our conversation. Looking over your papers, one of the topics that really popped out was your work on development. And this is particularly exciting at the moment to me and Kerstin, I guess, because Kerstin's just had a baby and I'm just about to have one. So I'm particularly curious to hear about some of your work on sleep in babies, how that differs from adults and how it starts to change.
So in general, actually, we are interested in our lab on information processing in altered state of consciousness. And that was the reason to also actually start with babies, because we don't expect the babies to be fully conscious, neither in the first weeks of life, nor, of course, prenatally. So what we started doing is to, for example, stimulate them before birth with nursery rhymes, see if they actually can learn this information, if they understand or if they learn basically the prosody or the melody behind these streams. And then we test them again directly after birth. So really with 2 weeks and 5 weeks afterwards, and see if their brain, their heart, or just their behavior in videos is showing us signs that they actually remember what they learned before birth. So this is one of the exciting things that we're doing right now.
So what kind of evidence can you see that they learned?
So what we saw so far is that actually they already with 2 weeks show a clear difference in how they basically couple their brain oscillations to the auditory stream if it is the mother's voice compared to another female voice. With respect to the rhyme familiarity, if they learned actually the prenatal rhyme, we don't have so clear evidence in the first study which we did. So we did not really see that the baby is tracked these prenatal streams more than neurons, for example. But this is something which is still ongoing. So we're now having the same project in a much bigger fashion and much more controlled than before, because according to the literature, there should be actually quite a bit of learning prenatally, which you actually could show after birth. The difference is just that most publications or most scientists work 3-4 months after birth. Start at that time, and we really try to start at 2 weeks after birth. And the big problem there simply is that they constantly cycle between sleep and wake. So basically, even if you stimulate them with a 7 decibel loud rhyme, they fall asleep every 30 seconds. So it's very difficult to actually record those babies.
That's really exciting about the babies and their learning. Particularly interesting being pregnant, thinking about should I be talking or singing or trying to teach the baby something at this point.
It's also interesting. So we were thinking also about combining those things because Manuel is also doing then longitudinal testings after birth that we would really be able to investigate the developmental of sleep spindles because they are not developed quite from the beginning. And if we get the chance that we have this kind of longitudinal testings, then we can really see which stage they develop their spindles.
So they don't have spindles at all when they're newborns?
They are not so regularly. They then, after a few weeks, are more pronounced. And then it would be nice to really see this development and maybe also the difference between those who develop them earlier and those who develop them later. And maybe also regarding the memory things that you then see those who perform better in the memory, that they are the ones where you see them earlier.
In our data set with the first weeks of life, we don't see spindles yet. And also the sleep staging is completely different. So if you basically try to sleep stage this data, also we are sleep lab working on sleep for many years, none of us could see anything. It's so different. And actually the experts in staging this sleep in babies, they look a lot on behavioral signs, like on video data, on respiration data, and not even rely so much on the brain data because it's really, really different. And also the states, of course, are quite different, right? Because you have not REM sleep in the strict sense, you have active sleep, quiet sleep, and wake, and you have the transitional phases, and everything is different in the baby. So we really try to learn actually how to do this. And we also started to develop like machine learning techniques which actually stage this data to at least have objective criterion what is what.
So that's fascinating that the sleep is so different than in the older child or adult. Can you just explain a little bit more about that? So you said they don't have slow sleep, they don't have REM, but they have this active and inactive sleep. So what is that?
Basically, the idea is that you only stage these three stages. So you stage active sleep, which then develops into REM sleep, where you have quite a bit of movement, where you have irregular heart rate, for example. And then you have quiet sleep, which develops into different non-REM sleep stages, N1 to N3. Where you have this deep and more regular breathing. So breathing is a super important criterion for all these stages. And then you have a lot of transitional sleep stages, which they call really transitional sleep, where you switch back and forth between these states. And you also have to keep in mind that in an adult, you expect around 20% dreaming REM sleep. And in the baby, you have up to 50% active sleep. So it's really very dynamic and much more active and much more, how would you say, unrestful than you would expect actually if you look at this baby sleep in the first weeks of life at least. Yeah.
So these 6 stages you said are characterized not so much by EEG but more by heart rate, eye movements, EMG. Is that the reason why they're not classified in the same way as the 6 stages when they're older, or do we know that the EEG is also different?
Actually, we did an EEG study on brain development in these first weeks of life, and we see that wake oscillations and spectra actually is pretty similar in the first weeks, but the non-REM sleep and the quiet sleep and the active sleep is changing tremendously already in these 3 weeks from the measurement point at 2 weeks to 5 weeks, with a huge shift in how the spectra and the oscillations develop. I have to say we are still digging there. It's not so easy to understand. There's also very few literature at these very early points in time. But we see that our classifiers basically completely fail to generalize from 2 to 5 weeks, even with the same babies. And as far as I remember, what our classifier got is basically the brain data and the heart and the eye data, but not, for example, video or respiration, what you also use for manual sleep classification.
And that's a classifier that succeeds in adult sleep.
Mm-hmm. Yeah. It succeeds to get close to what the subjective ratings can give you, which is not very impressive. It's 60 to 65% accuracy, epoch by epoch.
Yeah, I mean, it's already tricky enough to classify adult sleep into sleep stages in an automated way. So if everything is much more variable and changeable, then the classification goes down. And you said it was between even 3 and 5 weeks. Was that it?
Between 2 and 5 weeks, yeah. So we tested the same babies at 2 weeks, 5 weeks, 12 and 18 months. But at 12 and 18 months, we don't have much left because many, of course, drop out. And it was a non-funded project. So now in the follow-up, we now have actually a grant. We try to follow up as well until 18 months and hope to keep more into the protocol so that we actually know how this develops and that we can perhaps even predict from 2 weeks how oscillations develop and how language learning, cognition develops over these first 1.5 years. That would be one of the aims.
So you look for some kind of correlations between the sleep development and the learning.
Exactly. Sleep development, learning, and of course, stress and attachment, because it's probably very important to see in which environment the baby grows up, right? So like prenatally already, but those are the first weeks of life. So we also measure stress in the mother together with hormones and cortisol, and also attachment. So early bonding between mother or primary caregiver and the child, and see if this also actually affects cognition in the first 18 months.
That sounds like a big study. Very exciting. Why do you think the infant sleep is so different than to sleep in an older child?
Good question. I think because simply the brain is still developing and has to find its neural code and oscillations to communicate. I think it's really probably part of the pruning, which also takes place, that the brain has to find its streams and its highways. But it's a very good question. What exactly is the reason?
Yeah, it has to be a developmental reason. But if you read the older studies, it might even be a very simple thing that according to Manuel is doing now is really sophisticated. But I expect that also in former times we had the problem that maybe you didn't even catch all the periods which you were interested in. So, and also the quality of the recordings. I mean, Manu can tell you this story. It's really not the best quality as they move a lot, or it's not so easy to have an artifact-free recording. So this might also be a technical reason or a simple environment reason. And it's, or at least I was there a few times when you guys did the recordings. It's then always that the baby has to be held by the mother, or it's sitting in a maxi cozy. So its environment might impact then also on the quality of the recordings.
That's an important point what Kerstin says, because one of the restrictions is that you don't have so much control, right, over the baby, because one of the most important things is comfort for the baby. Otherwise, simply cannot record, because if the baby starts waking up and crying all the time, you could not get any data. So actually the compromise is always that basically the mother usually holds the baby also during the recordings, which is not so easy also experimental wise, but it is the best compromise, I think, still, because at least then it is feeling safe and is moving less, is crying less. And we of course also make the experience, as soon as the baby cries and the mother gets nervous, we basically can go home, because as soon as the mother is nervous, the baby doesn't stop crying anymore, and then everything is gone. And you have to imagine that in these very early ages, 2 and 5 weeks, the babies don't come to us to the lab. We basically have all the amplifier and all the stuff. We go through all the Salzburg County and record there, and it takes like 3-4 hours for a recording of 30 minutes. And if then the baby, of course, cries and doesn't stop crying, then we just lost it.
Wow. You must have very patient students working on this project. They're like babies.
Patient and passionate.
Yeah.
Patient and passionate. What do we know about sleep before birth? Do we know anything about sleep in the uterus?
I mean, there are some MEG studies where you really put the belly in the scanner, but I just know this is done in Tübingen, but I don't actually know exactly the results, what they found out.
Yeah, Preissl in Tübingen is doing quite a bit there. This baby MEG scanner, indeed. I think actually we don't know too much, because even a 50% REM sleep claim, which you have in sleep, as far as I know, it's just an interpolation. It's just a regression line where one expects, okay, at birth they have so much REM sleeps, and before birth they have 50%. So it's not measured. It's partly not measured data. It's modeled data, basically. So what I know actually from the Preissl studies, they didn't do much on sleep. They basically have classical event-related potentials, right? With simple stimuli, which you can repeat many times so that you get a nice mean of a simple response of the brain, for example. But with respect to sleep, to be honest, I don't know if they have brain data. I think it's more like probably heartbeat data. So how irregular is the heartbeat? And from that, basically, they make an inference if this is more like active sleep, which would be irregular heartbeats, or like more quiet and slower heartbeats for quiet non-REM sleep.
Yeah, I agree. The studies are going to be hard to do. I guess we can at least expect that it's very disorganized and sleep is getting more structured as the brain develops.
From my personal experience, I would say that there is already definitely a rhythm, and it's fitted to your own rhythm, and you might experience this as well. As long as you are moving, he or she is most of the time probably sleeping, and as soon as you are calm, then he has more space to move. Also, what Manu just said, that there are definitely no data about sleep and sleep measurement measurements. But if you still use activity, then there seems to be, at least in the third trimester, already a rhythm, which most of the time is adapted to the rhythm of the mother. I did still a lot of exercise. And I always had the impression when I was moving and I was exhausted, then he was really calm and maybe sleeping. And as soon as then I got relaxed, he started to.
It would be super interesting how much is genetic and how much is then basically learned, right? So if you learn basically that you move 16 hours a day to certain periods and 8 hours not, basically there is actually already a learning or shaping of the brain of the baby. But this is so difficult. There are so many factors which you cannot control, right? So you would need a probably sample with 1,000 children or babies to make a good guess if this actually has an effect.
Also the problem that you cannot really measure it in the end, because even with what we said before, what Preisler is doing with the MEG, I don't think that really can capture the brain activities. I would say the heart activity you might be able to capture, but that's it in the end.
Maybe they have these eventuated potentials, but it's very simple. You have to be lucky that something like the temporal cortex is close to the sensors, and then they have like a big plop that there is eventuated potentials. This looks different for mother voice than other voice, for example, but it's like really, really tricky to get out these basic effects even. So I expect like changes of sleep stages and so. Might be interesting. Good challenge for the next years.
I'm sure it would be very interesting. So Kerstin, earlier you mentioned sleep spindles and a link between sleep spindles and learning. Can you maybe first explain what sleep spindles are and then tell us about some of the work that you've done looking at their impacts?
So sleep spindles are really prominent sleep pattern actually, which as we said before is developed within the first weeks of development in babies also. So I would say between 6 and 10 weeks after birth, you can see them quite good. And it's a sleep oscillation pattern in the frequency range between 11 and 16 hertz. The core frequency lies between 12 and 15 hertz. And one of these key measures you see in light sleep, so in non-REM 2 sleep, which is actually the most dominant sleep stage. So we spend 50% of our duration in non-REM 2 sleep. And we know that, as I said before, even in the babies, we can see clear development, and also in the children where we actually did most of our work. So at the age around 8, 10, it is still developing. And I would say it reaches the adult pattern throughout adolescence up to, I would say, 16, 18 years, where you then also see this nice distribution over the cortex. So we mainly differentiate more slow sleep spindles in the range around 11 to 13 hertz, which are more frontally located. And then you have the faster ones, which are more parietally located. And these are actually also the interesting ones where Manu already 10 years ago could show that these are the ones which might be the most interesting ones for learning and memory. And that's actually also the interesting part, which we did the last years, that we tried really to longitudinally investigate this development. So we started to record sleep of children in the age of, as I said, 8 to 10 years. And then the same children were brought back to the lab then 6 to 8 years later when they were adolescents. And then we could really see how the sleep spindles individually developed.
So when you say how they individually developed, do you mean how the fast spindles and the slow spindles developed?
And individually, I mean that we not only had a cross-sectional study, so that it were different people, because it is very important that you individually adjust the frequency range also. So it is always then nice that you have one person at the age of 8 and then again at the age of 16, that you really then can see how it develops in one person, and not only that you compare different age groups which are then independent.
What did you observe with the development? How did they change?
The nice thing was that it was clearly seen that at this earlier age, so around 8 years, we still had this dominance of more slow spindles around 11 hertz, which were dominant in frontal areas. And it then really nicely moved more centroparietally and became faster by means of then around 15 hertz. And also, I mean, the coolest thing was in the end that we found that this development was really also related to the change in memory performance. So we did this classical word pair association task, so this declarative learning, which is like vocabulary learning, so what also you need at school. And those subjects who could perform better on these tasks were also those who developed faster by means of they showed this pattern, slow, fast spindle activity in a better way than the others.
So it's a clear distinction between the slow and fast. They developed more within the period that you looked at. Why do you think the spindles change?
I mean, in the end, I think it's not only the spindles, it's really the whole frequency range. Also, the things we discussed before about the spindles in these early 10 weeks of birth. I would say that it's simply that the brain really accelerates somehow the activity. And with regards to the spindle activity, also you have this more synchronized activity actually when you are younger. And then it's obviously distributed more to the parieto-occipital areas where it's then also getting faster. Maybe it's also about the distance between the generating areas, because we know that spindles are generated in thalamocortical loops. So maybe it's also that when the brain is growing, that the distance of these areas is also getting larger. So therefore, this accelerating takes part. But I think this is also really an open question. I don't know if Manu knows more about this, but then I really have to say it's not only the spindle activity which is accelerating. So also if we talk about the alpha activity in the range around 10 Hz, we also see this development that at the beginning it's more into theta direction, so slower, and then at around the age of 10 to 12, it's getting that you really see this peak like you see it in the adult brain, that you have this dominant alpha peak around 10 to 12 Hz. To put it together, I would say that there is a general acceleration, but interestingly also this differentiation between the slow and the fast spindles got more pronounced than the older you grow.
And do you think there's a functional significance to that distinction between the slow and the fast? Perhaps it would be good to introduce why spindles are important. What do we think they are doing? Why are they interesting?
The idea is that by sleep spindles, you really have this transfer from more short-term memory to more long-term memory. So this is the idea that you have a working memory space where you store the memory during learning. And then during sleep, by means of these sleep oscillations, the sleep spindles, there is this transfer that you really then locate the important memory which you want to store in the neocortex. And thereby you need this transfer between hippocampus and cortex. And therefore, we think that the sleep spindles are very important, but not only the spindles, it's then always the combination between the slow oscillations and the spindles, and also the hippocampal trophoid ripples. I mean, this we cannot really measure by our cortical EEG technique, but the slow oscillations, so this is actually also a big part now in our lab where Michael Hahn is focusing on, that we really want to see this combination, slow oscillations and sleep spindles, and it might be really these coordinated oscillations. When they work together, then it's really even better that this is really then highly coordinated.
So the spindles are somehow important for consolidating the memories, and we think that it involves transferring the memories between hippocampus and cortex, or at least coding them, integrating them into cortex somehow. And I think it's fair to say that the field in general doesn't really understand how this process happens.
No.
But the spindles are believed to be important. And there's a difference between the fast spindles and the slow spindles that you mentioned, right? So what is that, and how does that change across your longitudinal study?
In the earlier age, it's still a lot about the slower spindles. As we said before, that it's obviously the whole brain works at a slower frequency. And this still is for the children. We found really these relationships between memory performance, but also general cognitive abilities, where we use intelligence tests, that those children who have a stronger slow sleep spindle activity are those who perform also better in these cognitive tasks. And this then obviously develops until adolescence, that it becomes faster in frequency. And then especially these fast sleep spindles are more related to the cognitive processes. So it seems to be that this acceleration in the frequency of the whole brain, I would say, is somehow really related to this memory consolidation, but also not only to consolidation. It's really about general cognitive function. So we would say brain which has higher sleep spindle activity, especially in the fast sleep spindle frequency range, somehow also works better or is better connected, and therefore can really show a better cognitive performance communication.
This might be an idea of overdevelopment. You basically have to get to spindle types which are more and more distinct, and thereby you also gain basically another processing mode, right? So the faster ones seem to be more relevant for memory consolidation. The slower might take over another function, but you basically add another processing mode somehow. I think for the slow spindles, there's really not a clearer picture in the science at all what they are doing. Sometimes also come out as memory relevant ones, but often we don't find anything with slow spindles, for example. And as Kerstin said, it's really a gradual thing, right? So the frequency changes, and some point you come over certain hertz, and then you suddenly term them fast spindles. They're not so different than they were 6 months before. They just have a different frequency now sometimes, and topography also changes slowly. I think important point also is that also in our earlier studies, for example, we did EEG fMRI combined during sleep with auditory stimuli. And we saw that whenever you have a spindle, you also block out the outside world. So basically, in the most studies which we did, we see that information processing is ongoing through all sleep stages, even non-REM sleep, deep sleep, REM sleep. But when you have a spindle present during presentation of incoming stimulus, then the brain is completely blocking this information, which goes in hand with what Kerstin just said. We basically perhaps just have an inward attention somehow. So the brain basically processes information which is already in the brain for consolidating it. And it's not disturbed by the outside world because it just blocks out what comes in at that moment in time. And then, of course, you have a very interesting mechanism for evolution and for organisms, because you can completely block what's coming in for just a second and use this time for internal consolidation.
So how do the spindles block incoming stimuli?
That's a good question, how they block it. But I would say the evidence which we have is that it basically blocks information at the thalamocortical level. So basically in thalamus, where we say this is basically a gate to consciousness where information comes in, where all the senses have to go through, that already at this level, basically you just don't transmit and put through the information anymore, but that you block already at that very early level. And this you only can realize if you have basically a complete shift of oscillatory composition of the oscillating brain, right? And that's exactly what you have in spindles. You have this 12 to 15 hertz waxing and waning oscillation. And in that time, you have a processing mode where the thalamus, you don't have other inputs allowed, basically.
Yeah, so somehow they are preventing the thalamus, or the thalamus is preventing the other inputs. And that is because when you have a sensory input, it normally it comes from the sensory cortex, it has to get relayed through the thalamus, and then it goes back to the rest of the cortex, and that might be when you become aware of it, right?
Yeah.
And so what you're saying is these spindles, because they're oscillations between the thalamus and the cortex, somehow that oscillation is blocking things from getting through the thalamus at that time. And so earlier, Kerstin, you said that spindles were to do somehow with connectivity. And you talked about how the spindles, basically faster frequencies, were associated with better brain function in some way, more connected. Can you explain how they relate to connectivity? Is that known?
I mean, I would not say connectivity. I mean, also regarding that they really appear orchestrated in the same time like the slow oscillations appear. So I'm talking about connectivity between different frequency ranges. And that obviously, as we have a lot of spindles, it's not any spindle. It's really those spindles who are appearing timely, highly connected with the slow oscillations, which seem to be important for memory consolidation. Or at least when we differentiate between relationships where we try to see if higher spindle activity is connected to memory consolidation, it's not so exact. If we really then only use dead spindles who appear at the same time like the slow oscillations, this is then a more concrete and a more sensible measure for showing the memory consolidation performance. So it seems to be not only the spindles, it seems to be the coordinated appearance of these two oscillations, which is important.
So in addition to this synchronization, what Kerstin talks about, like the synchronization in time of slow oscillation and spindles, which seems very relevant in her studies, there is of course also connectivity in terms of anatomy. So you could also argue that of course thalamocortical connection is important for spindle generation. So it is a thalamocortical oscillation, a sleep spindle, right? So basically when you say, okay, spindles are basically a marker of thalamocortical connection, then you have a marker of connectivity between thalamus and cortex. And interestingly, also it's a very easy and basic idea. This seems to work out pretty well. So if you have stroke, for example, specifically one hemisphere is affected, then spindles only go down and in that hemisphere in sleep. If you look at post-comatose patients after severe brain injury, the spindles are a very good marker for recovery. So people which don't develop spindles, the post-comatose states, have a very bad prognosis. And the ones which have more spindles have a better prognosis. Again, with the idea perhaps it might indicate residual connectivity of the brain. So there are both dimensions, so the time synchronicity connectivity dimension, but also the anatomy connectivity dimension, I think, which is interesting with sleep spindles.
Yeah, so it makes them a very interesting marker to examine. And also we can pick them up with the EEG, which is what most of us normally use for measuring these things. So it makes sense, I guess, that the sleep field is a bit obsessed with spindles, and we are always measuring them and talking about them and looking at how they change. So let me just go back. Kerstin, you said the coupling between the different frequencies is important. And I know that you guys have done some work on this, actually coupling between spindles and slow oscillations and why that's important specifically. Do you want to explain that?
Before, maybe this is also, as we talked about development, this is really what we see then if we look into the differences between the child brain and the adolescent brain, that this synchrony between slow oscillations and sleep spindles really grow from childhood up to adolescence. So it seems, as we said before, this pattern of slow and fast spindles changes also this synchrony between slow oscillations and sleep spindles changing over the development. And again, it's related to the ability to do cognitive tasks. And I think it's really the thing that if we again talk about this transfer from short-term into long-term memory storage, it seems to be that we need both. We need the sleep spindles and we need the slow wave activity. And especially if these frequencies and these patterns are connected and appear at the same time, this seems to be then a marker that the brain is working in a smooth and synchronous way and thereby can then perform this memory consolidation easier.
And any ideas why that would be? And is there a particular phase on the slow oscillation when it should be better?
If you think about the slow oscillations, you differentiate up states and down states. And it seems really that those spindles who are connected to the up phase are the ones who are the more important ones. And also, as Manu said before, I think it's really important that we not only talk about this fixed frequency range, 11 to 13, 13 to 15. It's really important that you individually adjust this, that you really have a look into the brain activity of your subject, and then you see where are these borders, and then you can really differentiate also in the slow oscillation range, these individual adjusted frequency ranges, and check how these are then connected to each other. In our last papers, we did not really split again between slow and fast spindles. We rather went back and said, okay, we choose the individual frequency of the sleep spindles because especially in children, it's not so easy to detect who peaks in one subject. And then with this individually adjusted frequency range, we really found this connection to the slow oscillations that if they appear synchronously, then it's really the best situation for obviously having a good memory consolidation. But how development of this coupling between these two features is still not, I don't have an answer on this.
So maybe just to make a mental picture for people who are not familiar with what slow and fast oscillations are, you can imagine the slow oscillations as huge oscillations in cortical activity with, millions of neurons all firing at the peak of the oscillation and then a kind of pause in firing at the trough. And they are slow because they happen roughly every second. And so if you imagine in your mind a line that is like a wave going up and down every second, that could be a slow oscillation. And then the spindles that we're talking about are much faster oscillations, which are happening 10 to 16 times per second, depending on exactly whether they're fast or slow spindles. And they are more local, so they're only happening locally over particular areas of cortex. That means the amplitude is much smaller. So on top of your big wave, you imagine having kind of a burst of noise somewhere, and that would be what the slow oscillation looks like. And when we're talking about coupling between slow and fast oscillations, we're talking about whether those spindles always happen on the same part of the slow oscillation. Is it on the peak or the trough or in between somewhere? And what Kerstin is saying is that the more these fast spindle oscillations are coupled to the peaks of the slow oscillations, the better somehow. And I think you said that they get more coupled in that way across development. And this is associated with better cognitive function in a variety of ways.
And actually not from our own studies, but from the ones of our collaboration partner in Berkeley, we do know that it really then decreases again if you go to the other end of the age range. So So they investigated elderly people, and they then found that this decreases. So the synchrony between sleep spindles and oscillations went down again. So this is really nice if you bring this together.
So it's changing across the lifetime where it's becoming more synchronized and then less synchronized. Yeah. Mm-hmm. And I think there are so many unknown questions about this. I mean, firstly, we don't know why this synchronization matters, or do you have ideas about why?
If we think in terms of processing modes and different oscillations, right, then you need to communicate between the different processing modes and to basically transfer information. So somehow I think you could picture this nesting of oscillations in each other, or the synchronization of different oscillations, as a kind of a communication mode where they basically can interact. And therefore, I would say this is something which is needed sometimes. And on the other hand, of course, you don't want to have too much overlap. This is work of Wolfgang Glimisch, for example, always talks about golden mean and about specific relations of oscillations to each other, so that in most of the time, the oscillations can be completely distinct and do not disturb an overlap, right? Because if you say the different processing modes or different things are done at different oscillations, then they, of course, should not all the time overlap. They only should overlap at distinct points in time when they need to exchange information. So this would be like a rough picture in my mind. But of course, also there are many unknowns. But it would be one idea, I think, why you need synchronization of oscillations from time to time.
So do you mean like each frequency is maybe dealing with a different kind of information or dealing with information in a different way, and then occasionally you need to exchange between?
Yeah, like in a very easy way, you need, of course, oscillations which set priorities, right, with focus. And put attention somewhere. You have all the senses coming in. You have all the memories which you basically all the time have to access to make sense out of the information. So there are so many things going on, and the network somehow has to do this all in parallel. So how does it realize this? And I would say you best can realize this with different oscillations, which do not overlap too much, but when it needs to overlap, then it touches basically and synchronizes for a short time. This is at least one idea which I have when I think about oscillations, and I think that's one plausible theory about that.
I think that's a really interesting suggestion. I haven't heard that before. I guess it maybe maps onto the fact that the different oscillation frequencies are generated by different areas in the brain, different structures. So that would be consistent with the idea they are carrying out quite different processes.
And as you mentioned before, that of course the speed of oscillation is somehow related to the network size, right, and to the traveling time. So if you think about long range connectivity in very frontal and very occipital areas, of course the traveling time between those two areas is longer, so the oscillation which you will get there is slower than in a very local oscillation in the temporal cortex, for example. Neurons very close to each other have to fire. We have much shorter loop times, so they interact in much quicker oscillations. So it's again a very simple idea, but in general I think one can use this to guide a little bit this idea how oscillations are architectured.
So could that suggest that the slow oscillations are important for long distance communication in the brain, and the spindles are important for just these short, maybe transitions from hippocampus to cortex?
I think in a simple way, yes. Yeah. And also I think makes sense for sleep. If you think that in sleep you switch to a processing mode where usually things get less complex and big areas, part of the brain, should communicate and restore processes. I think this makes a lot of sense to me, because when you do sensory processing, I see a visual stimulus. Of course, I need my occipital cortex being highly engaged and process local information. In sleep, I might not have this anymore. It might be more about global interactions. So this would fit the picture.
Yeah, that's really interesting. But let's just go back for a minute to the fast and slow spindles. So, Kerstin, you said they become more distinct frequencies across development, and then they are associated with some kind of cognitive processes, right? So they're beneficial. Can you talk a little bit about the difference between which things fast and slow spindles were associated with in your study?
I mean, I would say that they are mainly associated with declarative learning. We also did a lot about motor learning, but we always found that they are really more related to this explicit declarative knowledge, by means of that you really have an explicit knowledge about what you are learning. The classical way, as I said always, is vocabulary learning. So as long as you have this kind of memory, I think you most of the time really find a connection with sleep spindle activity. If you then go into more the implicit and procedural areas, it's not so clear anymore. anymore. So I would stick it really to this decorative learning performance, that it seems to be the sleep spindles as well as low oscillations are important. Also, if you think about this decorative and explicit learning, it is mainly located in the hippocampus, and therefore this is also the reason why we think that it is related to sleep spindle activity. As we discussed before, the generation of sleep spindles, this fits actually quite well. And only that kind of motor tasks like classical finger tapping tasks, where you also have somehow at the beginning an explicit knowledge about, especially at this stage, then you also have the connection with sleep spindle activity. But as soon as you move into something like an automatized process, it's not so clear anymore. What is then also about sleep, what is enhancing this kind of learning. And regarding, again, the question slow and sleep spindles, as Manu also tried to explain before, I think if we talk about the developmental thing, it's clear that as the kids have more of the slow spindle activity and the slower activities in general, the whole brain is obviously in a more slower frequency range, then there we find these connections. But as the brain gets older, it's obviously more pronounced in this fast frequency range. And in the adult brain, we don't see these slow spindle connections with memory and general cognitive performance. So this is really restricted to the child brain. And it's really, as I said before, I really would also like in the literature that we focus more on this individual range and not talk too much about slow and fast spindles, as it's obviously really different in which age group you are. And to be honest, I by myself, I very rarely see in one power spectrum these two peaks that you really can have both frequency ranges.
So do you think that slow spindles are doing something different than in the adults and we just haven't worked out what it is, or they are just having no function in adults?
As I said, I'm not so sure if there is really a difference or if it's then really about the borders we are using. So because normally we very strictly say, okay, 11 to 13 is slow and 13 to 15 is fast sleep spindles. And we do not really prove this by individually adjusting these frequency borders. So I would expect even for our own studies, if we go back in this data set and really check what is the core frequency range, which definitely might be faster in the older adults, maybe we should really not focus too much on this differentiation, so more on an individual frequency range for the sleep spindles. But sure, if we try to do this, and I also have to say, we sometimes have this situation that you really have nicely two peaks, then there should be a differentiation, but I have no clear answer what's the difference.
So it's hard actually sometimes to separate what's fast and what's slow spindles. But you do have some work showing that the fast spindles are more associated with memory consolidation.
And also we talked before about this connection between slow oscillations and fast spindles, that especially the fast spindles are then connected with these upstates of the slow oscillations. And if this is a high coherence, then we also see these connections to memory consolidation.
Exactly. And you also see that they have different topography, right? And that they respond differently in the menstrual cycle. And so there are many, many differences between these two types of spindles. The interesting thing is that I think most of us still don't know, or nobody really knows, if they also have a clearly different function. And I think this is the big mystery. But yeah, I did not come across data or publications which give me a good idea of the slow spindles. They're still a big mystery, I would say.
Yeah, so for some reason there's more work on the fast spindles, and that's probably because the fast spindles are often more correlated with memory consolidation. And as I understand it, some of your work shows that the slow spindles are correlated with more general cognitive function, but not just memory consolidation.
But especially in the child age. And there I have to say we really almost didn't find any fast sleep spindles. So if we really stick to these frequency ranges, this was in this publication 2014, we in the end skipped then the fast frequency spindle range because there was simply no existing. So that was then the reason why we really focused on the slow spindles, and therefore we found this relationship between slow spindle activity and general cognitive performance by means of the intelligence.
And what kind of age range is this?
It was 8 to 10.
Okay, so we don't know at what point after 10 this changes as they develop.
It was then really clearly developed around in the age group between 14 and 16. So it has to be really this pruning which develops obviously during adolescence.
Okay. So the fast-slow distinction was developed, but the slow spindles were not so important for anything.
Yeah.
Yeah. So there's a lot more to understand about spindles and about development, I guess.
Yeah.
So you really covered a lot of things. Let me just say thank you very much. I really appreciate it. I learned a lot.
Thanks a lot for also inviting us, and let's keep in touch.
Thanks a lot.
You've been listening to the Sleep Science Podcast with me, Penny Lewis. My guests today were Professors Manuel Schabus and Kerstin Hoedlmoser from the Center for Cognitive Neuroscience at the University of Salzburg. Our producers were Sophie Smith and Bianca Stretta. If you've enjoyed this show, please consider subscribing to the podcast or liking us on Twitter. We're planning a Q&A session for the last episode of this series, so if you have questions about this episode or anything else related to sleep, please send them to us at #SleepSciencePodcastQ&A. Thanks for listening and see you again soon.